In the prior section of this part of the lecture, we discussed the size effect on the electronic structure of atomic clusters that exhibit a discrete phenomena. In this section, we will explore the effect of such small size on the current voltage characteristics that is known to be linear on the macro scale. To illustrate the impact of the quantum confinement on processes, let us compare the current voltage characteristics of a conventional electric circuit with a small metal or semiconducting cluster that we described earlier as an artificial atom or quantum dot. We consider first the macroscopic electric circuit. The current that flows through the cable in response to an applied voltage follows Ohm's law. In other words, changes linear with the applied voltage. In order to measure but not to interfere with the conduction properties of an artificial atom, we couple a macroscopic circuit very weakly via two tunnel junctions to it. The tunnel junctions gives us the possibility to load and unload electrons in discrete fashion to and from the artificial atom. The consequence is an IV characteristics that exhibits a staircase behavior also known as Coulomb staircase. The Coulomb staircase phenomena of current flow as function of the applied voltage involving a small metal cluster of atoms shall here be briefly explained. As pointed out, a small cluster that exhibits electronic energy discretization is weakly coupled to the source and the drain via two tunnel junctions, represented here by the tunnel resistance RT on both sides of the cluster. A tunnel junction is an ultra-thin insulating film with thickness on the order of a nanometer that classically inhibits current flow but provides the quantum mechanical probability of single electrons to tunnel through the barrier. We can attribute a capacitance to the tunnel junction which acts as a dielectric. Coupling a metal source through a tunnel junction with a quantum dot, as depicted here, electrons will tunnel onto the dot until all energy levels that are exceeded by the highest energy level of the electrode source are filled. This is indicated here with the blue dot-filled electron levels on the quantum dot in relation to the red electron sea of the source electrode. Filling the quantum dot up with electrons produces an electric potential that inhibits further electrons to tunnel through the barrier. This aspect is reflected in the energy diagram and indicated as off-state. In order for electrons to flow through the electric circuit, the bias has to overcome the barrier to populate a higher energy level of the quantum dot. This defines the so-called charging energy, EC, depicted here as the on state. With integer multiples of the charging energy, higher electronic states can be reached. The consequence is a discrete step-like current voltage characteristics. There are two forces in nature that could wash out this effect easily. One is based on Heisenberg's uncertainty principle, which states that there are fundamental limits to the precision with which certain pairs of physical properties such as energy and time, and location and linear momentum can be known. I call it here quantum noise. If an energy barrier is exceeded by the quantum noise, electrons can escape spontaneously and hence not be controlled. To avoid such transport, we require a tunnel resistance that exceeds by at least an order of magnitude the ratio between the Planck constant and the elementary charge squared. The second possibility for a washout of the Coulomb staircase effect is given by thermal noise. This is the vibrations of the core atoms. that can activate an electron into a higher electronic state, which allows it to travel through the barrier. To avoid this, we require that the charging energy exceeds the thermal energy kBT, where kB is the Boltzmann constant and T the absolute Kelvin temperature. This explains why very low temperatures are required to observe quantum steps. For practical applications, a gate electrode is added to the circuitry. By capacitive coupling the gate electrode to the quantum dot, the energy levels on the dot can be shifted on demand and thus their current modulated. Practical applications employing the single electron transport mechanism are on the horizon. This brings us to the end of this part of the lecture that was provided in 2 sections. Recognizing with the atomic structure of matter that energy occurs in discrete form, a new field of science evolved, called quantum theory. The quantum theory provides the basis on how atomistic building blocks interact with each other and underlies all material properties from colors to conduction, from elasticity to volatility, by defining the electronic nature of materials. Starting with the Bohr model, we recognize the discrete energy signature of the atom. Looking at small number atom clusters, also called artificial atoms, we notice the energy level gaps to shrink steadily with increasing cluster size until the energy levels become indistinguishable in electronic bands. From a practical perspective, most notable is that the energy discretization is still existing on the low nanometer scale. It is the energy discretization in nanoscale materials that offers vast opportunities in electronics and sensing. We contrasted the small-size quantum nature of condensed materials to the gas system, for which we consider the number of particles within a given volume. Also for such a system we found that size matters. We noticed that equilibrium conditions are put in questions for small-size systems, where fluctuations become too large to be ignored. We will later see that these fluctuations are necessary for processes such as diffusion, chemical reaction or assembly to occur. Looking closer at clusters, in particular metal clusters, we found a size regime of a few nanometer radius in which a conductive spherical metal particle transitions to a semiconductor. We called particles on that scale, in which the semiconducting band gap is tunable with size, quantum dots. As a critical size determining parameter, we introduced the Bohr radius for quantum dots. Next, we analyzed the conduction properties of quantum dots in an electric circuit and found the discretization of the current voltage characteristics. For so-called Coulomb staircase to work, it requires control over quantum noise and thermal noise that can be obtained, respectively, with a nanoscale thick tunnel resistance and charging energy that exceeds the thermal energy. This effort of suppressing quantum and thermal noise we introduced as Coulomb blockade. This brings us to the end of this part of the lecture that was provided in 2 sections. Recognizing with the atomic structure of matter that energy occurs in discrete form, a new field of science evolved called the quantum theory. The quantum theory provides the basis on how atomistic building blocks interact with each other and underlies all material properties, from colors to conduction, from elasticity to volatility, by defining the electronic nature of materials. Starting with Bohr model, we recognized the discrete energy signature of the atom, looking at small number of atom clusters, also called artificial atoms. We noticed